Hello, and welcome to the first part of this multi-part series on how to build a professional control room. Now, I have been diving deep into Philip Newell's book, Home Recording Studio Design, and this is a thick 750-page book, and part of this book is that he goes through the entire design and build of a control room, and this was built, I think, in Moscow in Russia, and it was built as a Foley studio, so there's a control room and a live room. For this series, I'm going to focus just on the control room because I know a lot of you out there are interested in great mixing, mastering, and maybe single room home recording studios, and a control room design like this would work well for all of us one room, single room producers who want to elevate our acoustics and isolation and just level of professionalism to that next level. So that's what we're going to talk about. Today is going to be mostly about the isolation shell of that control room. And then part 2 and maybe even part 3 will go into the acoustic design and the more nuanced design of the speakers and the front walls and all that stuff. It's a ton of information, so I had to break it up into separate videos. Before we jump in, if you're going down this road of building as professional of a control room, recording studio room in your home as possible, then check out my free soundproofing workshop. It will go in depth into the best ways to do this. And that is at soundproofyourstudio.com/workshop. That's soundproofyourstudio.com/workshop. All right, let's jump into this lesson on how to design a professional control room, part 1. So the very first thing a professional studio designer would do is look at the site selection that the studio owner wants them to build in. And a good studio designer worth any amount of money you pay them would be able to tell you if the site selection is a terrible idea, meaning it would be so hard to isolate that it's not even worth it. And for us home studio musicians, this is a huge problem. We tend to build in whatever we have, and we're kind of have our cards stacked against us before we even start building. But for the pros, they know better. So in this case, this was in a great site selection. It was already in an existing building. It was on, I think, maybe even the 7th floor of something, but it was an entire massive concrete room. In this diagram here, you can see that the existing structure of just the control room, which is what we're going to be focusing on, Philip Newell said it was about 7 meters by 7 meters, which comes out to 23 feet by 23 feet. So a good floor space just to start with. I know that's a cube, but remember, we're building inside of it. This is just the area of the control room. And then the other crazy thing is that the ceiling height was actually 8 meters, which comes out to roughly 26 feet in ceiling height of the existing room. So this is a massive space, something unheard of in the home studio recording market. The other thing is the walls were masonry walls. So the floor was a concrete slab laid, even though it was on a building, it had a concrete slab. For the floor, it has masonry brick with like concrete plaster, it looks like, over top of it. And then the ceiling was a concrete ceiling. So you're starting out with already a great isolation shell to begin with. So the first step in designing this recording studio control room is to get the isolation walls in place. So we have our exterior walls, but remember, in soundproofing design, we always want to have a 2-wall system. We have our exterior walls and then we have our interior walls. And what's going to happen here is Philip Newell actually built the interior walls with a 5 centimeter to 10 centimeter gap all the way around the exterior walls, so that there is a gap between the interior and outside walls. That 5 to 10 centimeters roughly equates to about 2 to 4 inches in the imperial system. And he builds all of his isolation walls from concrete blocks that are filled with sand. And that's going to give you a tremendous amount of mass, which is what you need to stop sound. You know, these could be cinder blocks here in the US is a typical example. They're usually 8 inches by 16 inches, and then you would just fill sand in the middle. Now, these block walls in his design go up to 4.5 meters. I think he figured we didn't need to go up to the full 26 feet, and that would add a ton of costs. So he kind of put it about that perfect height. Now, 4.5 meters is just shy of about 15 feet tall. It's 14.7 feet. But you're getting your exterior ceiling at a very high height. Again, most of us don't even have 15 feet to even begin to think about working with. So this is really what sets apart the pros from us amateurs over here trying to build our home studios. But don't get discouraged. We're just going to learn from this as we go. And I think it's really cool to see how he does it, and then we can try to apply it to our own home studios. I noticed in his design that he has this, cube outer area roughly that he says in the book. He said that the control room took up about, that 7 meter by 7 meter space. But in the final design that he shows in the plans, he doesn't give a lot of dimensions, but just by looking at it, I figured it was about a 5-degree angled wall on both of the concrete walls on the inside of the control room. And there's a lot of debate over, do you need to angle your walls? Do you not need to angle your walls? And I know Philip Newell kind of falls somewhere in the middle. He certainly does tend to sense that by angling the walls, you can kind of disrupt the axial modes bouncing back and forth. Now, I know there are books like the Master Handbook of Acoustics that almost would refute that entirely. And I actually lean in the sense that modes don't really get affected by the angling of walls. However, an extremely thick angled wall like this concrete block where those low frequency waves hit it and are reflected right back, they're not actually absorbed or they don't go through that wall. If you think of our traditional soundproofing walls with just, drywall and 2 layers of drywall and then a gap and whatever, it's still not a very massive system compared to a concrete block wall. So I think he is making sense here by saying if we angle 2 of these concrete block walls on the sides, we will help a little bit with disrupting the modal area of the axial modes bouncing back and forth left to right. Now, front to back, he kept those straight. So, we'll talk about the acoustics later on in this series, but I just wanted to point that out, that these walls were angled in his design. And so I angled them as well in my design, trying to copy what he's doing in SketchUp. And you can see that here in this diagram. I will say too really quick that Philip Newell is not a fan at all of room ratios. He doesn't use them. Part of the reason he has the luxury to build massive isolation shells and incredible acoustic shells that absorb so much of the low end that designing within room ratios is not necessarily even needed for him because he's absorbing so much of that low end. I would also say that he said that room ratios, and I agree with this statement, assume an infinitely rigid structure which is impossible in real life. So therefore, every room ratio you use is going to be inherently off. And because those room ratios to begin with are so accurate down to, even the 1/2 of an inch, it's hard to imagine that in practice building a room to a room ratio would give you the same results as the calculator had predicted. But that's a whole nother video. I've talked about that in the past, but I just want to point that out here. So next up, we have our isolated concrete floor, or a floating floor is what it's commonly known as. And Philip Newell doesn't mess around. I mean, when you're building these professional studios, they're going to float the floor, even though it's on a concrete floor to begin with. The budgets are so huge, millions of dollars invested, and then also millions of dollars that could be gained in profits from a studio like this, where any sort of sound leakage that could pass through the floor, they're just going to float the floor because why even deal with that? So for us home studio people, I usually say don't float your floor because it's costly and it's usually not necessary. I mean, especially if you're doing a single room studio on a concrete slab, not much sound can get through the concrete floor. But for these situations where you're running, subs that go down to 20 hertz and this is a super high level professional studio, yeah, float the floor. And if the budget's there, he's definitely going to do it. So this is how he does that. And this is really fascinating. I love this aspect of this book more than anything else I've ever read, because everything else I've ever read talks about isolation in terms of springs and air gaps. And Philip Newell really starts to take it to another level of understanding that the mass spring mass isolation system really can be made of any material. That spring in the middle can be mineral, it can be foam, it can be air, it could be freaking water if you could figure out how to do it. But the idea of the physics of it being a spring of many different materials, I think is really amazing to me, because we get so obsessed with specific materials that we hear about and specific design criteria, and Philip Newell kind of uses the science and says, hey, there's a lot of options here. So in this design, and I think he does this a lot, and it's something that I will do when the budget is there, is using mineral wool as the spring. So he starts out, if you can see in this diagram here, with that layer of mineral wool laid right across the existing concrete deck. And that's going to be 10 centimeters, which is roughly 4 inches, and it's 70 kilograms per meter cubed, which comes out to roughly 4 pounds per cubic foot. So that's 4 inches, 4 pounds per cubic foot in imperial, and then 10 centimeters, 70 kilograms per meter cubed in the metric system. And the thickness and density of that spring is fairly important for this design, because when you put all that weight on top of it, it needs to compress. A percentage of that mineral wool needs to be compressed, but not all the way down to 100%, because then it defeats the whole purpose. If the concrete slab pushes the mineral wool all the way to the floor, then you've short-circuited the system and it fails. So that's what's kind of tricky about this, but this is a system in his book that he already says, hey, this will work. You'll get a slab that resonates below 20 hertz, which is the lowest we can hear as humans. So if that slab is resonating at a frequency lower than we can hear, then we're not going to hear it. So that's the beauty. It can get picked up by microphones, but no one in the world can hear it, so whatever, except for dogs or other animals that hear that low. After the mineral wool, he says to put down a layer of plastic sheeting. This is just so that the concrete, when it does come on top of the mineral wool, none of it will actually get down into the wool and start to short circuit the system or get tangled up in the mineral wool. After that plastic sheeting, he says he puts 2 layers of OSB sheathing. I would imagine these would be really thin, because you don't really need them for mass at this point. And they're really, he said, so that the workers, when they're laying the concrete slab, they don't like trample all the mineral wool underfoot and kind of reduce its ability to hold the slab, so that it'll create a flat surface that would spread out the pinpoint pressure of them walking on the mineral wool. So that's 2 layers of overlapped, remember, all the times overlapping seams, so you don't have any air leaking through, of the OSB. And then finally, after you've done all that, you can pour. So you put rebar and everything in the floor, and then you pour your concrete slab over top of the 2 layers of OSB sheathing. And that is your floating concrete slab. Pretty cool. And that concrete is 10 centimeters, so it'd be about 4 inches of a concrete slab sitting on top of all that. Now, it's important to notice that the concrete slab needs to have an air gap between the isolation walls, otherwise it's not a floating slab. If it's touching the isolation walls, it's connecting everything else, because the isolation walls essentially are, as far as I could tell in his design, these walls were sitting right directly on the basement, or not basement, the concrete floor. You can put mineral wool underneath these walls as well, so that the walls themselves are floating, but I don't think he did that in this case. He did use some material like silomer, I think it was, in the wall design above the concrete floor to actually decouple it from the rest. So that is an important point that I want to make sure you know. So with that air gap around the isolated concrete slab, remember, this could be another 5 to 10 centimeters air gap around that, and he puts mineral wool angled upwards around the entire air gap. So you can see that in this diagram here, that the mineral wool will help the concrete. So you'd put that in before you pour the concrete, and the concrete would hit the mineral wool and not actually go through it and touch the actual side of the walls there. So that's another important aspect of this design, to keep that air gap around your slab. Lastly, we have the isolated ceiling joists. So these isolated ceiling joists are, he doesn't go into this in the book per se, but he does talk about reinforcing ceiling joists so that they can hold the load of the ceiling. And these look like pretty big joists. So this is how he designs these ceiling joists that need to span across. You can see that there are 2 20 centimeter by 5 centimeter. That's going to be a 2x8 in the United States in imperial units. And you would glue and screw or nail those 2 pieces together. And then you'd put 2 2x4s, one on the top, one on the bottom, which would come out to 10 centimeters by 5 centimeters in metric units. And then finally, 25 millimeters of plywood on both sides of this beam. And that would be 1 inch of plywood in imperial terms here. And so these beams are going to be super, super strong. They can span greater lengths, and he uses them both for I think his exterior shells and his internal shells where needed. I will say, with this level of design, I know Philip Newell, his son, is an engineer, of course, so his son helps him out probably with the engineering side of this. But just knowing the stress that can be put on these beams with all the weird weights we're putting on them with acoustics and isolation design, it's important to consult with an engineer, a structural engineer, if you're doing this at a high level. Here you can see the finished beams as they were put into the interior isolation wall, so just basically framed into the concrete walls at the very top. And like I said before, you might be wondering, okay, he's attaching his exterior ceiling, like inner shell ceiling, to the interior walls. And doesn't that seem like counterintuitive? But again, remember, he put those silomer little plates. I'll have to look back at them, but they're in the wall, so that the wall itself is sort of isolated before it goes down to the floor. And I remember in the book he said that he didn't isolate the wall at the floor because he was worried that the concrete could seep down and touch that, somehow short-circuiting the system. So he instead put isolation plates for the walls higher up in the wall system. And you can actually see in his book, there's little gaps in the walls where these isolation silomer or Solomer plates are. So it's basically, I think, like a thick piece of rubber that essentially decouples the wall at that level. So your isolation beam is sitting on the internal structure, but sound can't come up from the wall. And then also, this is such a thick wall that, and you'll also see that we're going to do so many internal acoustic walls that the isolation becomes part of the whole system. The acoustic wall and the exterior isolation systems work together to help with the overall isolation. So this is how he did it. I assume you could have done the joists all the way to the exterior wall and tapped them in somehow with some sort of engineering, but I'm sure it also was easier just to throw them on the interior walls. All right, so that concludes this in-depth video of the isolation aspects of a professional control room design. So hopefully this has opened and enlightened you to how intense it can get, especially with floating a concrete slab, building really massive block walls, all that stuff there. So in conclusion, I think I want you to know, like, hey, you shouldn't go and try to copy this. It costs you a fortune. Sure, if you have the space, you have the money, do it. But for us people doing this in our homes, we can kind of look at it like, okay, using concrete sand-filled blocks is going to provide excellent isolation. And I would recommend it if you have the budget and the space, but you lose 8 inches if you're doing one wall. And if you're doing two, you lose, 16 inches plus an air gap. So that's a lot of space to lose. And then we can also look at the size of the room, just how much space is going to be used for the acoustics of the room. And then we can kind of understand, like, okay, when we're doing our home studios, we'll never be able to achieve the same level of acoustics that they have at these big, beautiful studios. But can we get close, or can we understand the limitations of our home studio? And when a studio designer says, hey, adding more space for your isolation and your acoustic systems will lead to a better sounding room, but you don't want to give up that space, you now know why there's this give and take play in home recording studio design, which I am finding more and more is making my life more difficult than Philip Newell. Because when we have smaller budgets and smaller rooms, the acoustics, we're starting at such a difficult place to begin with, and we need to do so much more to even try to get to that professional level. So keep all that in mind. Get the biggest room possible. Try to find the most isolated room possible that you can to start with, and you'll be light years ahead in the long run. All right, this was a long little video as an intro. Next week, I'll be doing part 2, and then maybe even part 3 in the 3rd week through the entire control room design. If you are going down this journey of trying to build a soundproof studio, then check out my workshop. It's super helpful in taking this type of knowledge and then putting it in more realistic terms of how you can do this yourself on a reasonable budget. So that is at soundproofyourstudio.com/workshop, soundproofyourstudio.com/workshop. I'll see you all next week for part 2 of the series.